Welcome, boys and girls, to ViViMaT, the Vienna Virtual Materials Tribology Workshop. Our next speaker, Shiva Raghuraman, got his PhD in mechanical engineering in the group of Johnny Felts at Texas A&M University. He is currently a postdoc in the Functional Atomic Force Microscopy group headed by Stephen Jesse at the Oak Ridge National Lab. Don't forget to scribble your questions to him in the comments section below, and I'm going to pay close attention to this talk since I'm currently also writing something on speed dependence. Shiva, you're up right after this. Coatings is a peer-reviewed journal of coatings and surface engineering published online by MDPI on a monthly basis.
And now, atomic scale wear.
Hi everyone, I'll give a short talk about our work on friction and wear at the atomic scale. We look at how normal and lateral forces influence monolayer wear on graphene oxide, and we propose an elegant model to understand different types of wear. You can access the paper with this link. My name is Shiva. I'm currently a postdoc at the Functional Atomic Force Microscopy group at CNMS at Oak Ridge National Lab. I did my PhD under the supervision of Dr. Jonathan Felts in the Department of Mechanical Engineering at Texas A&M University. My previous and current research are centered around scanning probe microscopy, where I develop techniques that will enable us to quantitatively investigate processes driven by heat, light, electric fields, and force at the nanoscale. The work that I'm going to talk about today was done when I was a grad student at Texas A&M with Dr. Felts, and the funding came from NSF and Texas A&M Engineering Experiment Station. Moving on to the talk. Sliding induced wear is seen almost all around us, from the cars we drive, the machineries for manufacturing, and in marine environments. Friction and wear have a significant economic impact, and nearly 25% of world's energy consumption can be attributed to it. Efforts to understand the mechanism of wear across spatial scales, from macro down to the atomic scale, are of high impact for this reason. If we were able to understand and control wear, we could rationally design materials and interfaces to mitigate damage and save the dollars spent by making systems more efficient. However, wear and friction are both extremely parameter-rich spaces or concepts, where several factors, including the chemistry of interfaces and contact, environmental conditions, stresses involved, sliding speeds, all have confounding effects. For example, at the macro scale, wear is seen as a phenomenon that is not dependent on velocity. This is typically called the Archer type wear. Experiments on the nanoscale, however, show that sliding speed is extremely influential on the wear rates, and wear is exponentially dependent on the applied force. There are several models to explain wear, but the problem is that they work only well on the specific systems they are modeled on. This is understandable, as many experiments even show evolving friction coefficients as the wear is progressing, which means the chemistry evolving at the contact is critical to understand the mechanism of wear. On the other hand, friction, meaning sliding without any wear, is a very well explored concept, and its physical origins are very well understood. The widely accepted model for friction is this Prandtl-Tomlinson model, which explains that friction originates as the atom moves across the energy corrugation of the surface, resulting in this kind of a stick-slip motion. This has been experimentally verified, and the friction coefficients agree very well with theoretical predictions. What we want to do is unify the current understanding of friction and wear and tie it to chemistry in an abstract way that can shed some fundamental insights on the mechanism of wear. In addition, we also need to understand how the different forces, the normal and the shear force, influence wear. Our work aims at providing a general picture on the mechanism of wear. The model we propose is dynamic and hinges on seeing the evolving interface as reversible bonding between the interacting atoms. Our experiments were performed on graphene oxide, but they can be, or this model can be applied to any arbitrary chemical system. First, I'll give a qualitative picture of our model with the help of this simulation. In this simulation, the gold spheres are carbon atoms on graphene. The dark blue spheres are the silicon from the tip. The dark purple spheres are oxygen bound to the tip, and pale purple or pink spheres are oxygen groups bound to the surface. In this video, notice the molecule on the bottom left that is jumping between the tip and the surface. Basically, it's bonding to the tip and then unbonding from the tip and bonding to the surface. So this bonding and unbonding process proceeds as the tip slides from left to right. And eventually, when the tip slides, the molecule is carried over and it hops the lattice space. This is the picture that we are proposing for the mechanism of wear. From a chemistry perspective, we then have three thermally activated processes in our model. Bonding, where the molecule interacts with the tip. Unbonding, in which the molecule interacts again with the substrate. The third process is the hopping, where the molecules are bonded, which are bonded to the tip, move along with the tip in the sliding direction. Hence, this picture is more dynamic, where all these three processes happen simultaneously, and each of them have their own rates and energy barriers. From our experiments, we can back calculate these energy barriers and other reaction parameters. Mathematically, we can describe each of these processes with this Arrhenius type equation. Here, E is the energy barrier, V is the activation volume, T is the temperature, and this term P is the pressure distribution around the tip, or pressure distribution at the tip surface contact, where R is the distance from the tip center and T is the dwell time, or the cumulative time the tip spends on each spot as it slides across the surface. Unbonding takes a similar mathematical form, except it has its own energy barrier. The rate of hopping or wear is independent of pressure, but it is dependent on the energy corrugation of the surface. The rate of change of surface composition during sliding can then be given by these equations. In the absence of sliding, where the velocity is zero, these equations just boil down to the normal force dependence. We do pull-off force experiments, and we fit those data to the zero velocity condition to obtain the energy barriers for the bonding and unbonding. We also do sliding experiments at different velocities, and we use the full-blown expression to figure out the barrier for wear or hopping. So our pull-off force experiment results are here, and we did these for temperatures from 30 to 60 degrees Celsius, where the substrate was globally heated. And we also did this for a wide range of tip forces from 10 nanonewton to 125 nanonewton. The results of the experiments are shown here, and they agree very well with previous estimations on graphene oxide. The key observation here was that more species bond to the tip with increasing normal forces. So the normal force drives the bonding and increases the population of species bonded to the tip. For our sliding experiments, we implement a two-step routine to measure the chemistry through the friction signal. Here, on the movie on top left, there is a drive scan. The first step is a drive scan, which makes the feature on the surface, which cleaves the functional groups. Then we do a measure scan at a lower force, which is not going to damage the surface or remove bonds from the surface, which takes this larger scan. From this friction scan, we can identify the modified region and its surrounding region. So what we do is we take the friction of the modified region and divide it by the friction of the unmodified surrounding region, and we call this the relative friction. And from our previous ex situ spectroscopic studies, we have shown that this relative friction signal linearly correlates to surface chemical composition. And when we repeat this routine over and over again several hundred times, by gradually incrementing the velocity after each iteration, what we end up with is a velocity ramp experiment, like shown here. On the left, you're seeing a series of friction images, and on the right, you're seeing the change in chemical composition, or the relative friction percentage, which is the percentage of oxygen groups left on the surface as a function of the velocity of the tip. So we performed velocity ramp experiments for normal forces between 15 and 300 nanonewton, and we obtained energy barriers from each curve and plotted as a function of normal force, which is what you're seeing in figure B. There are two important observations here. First, if you notice the red curve, there is no wear up to about 6 micrometers per second, and then the wear accelerates. So there is a critical velocity below which there is no wear. And this critical velocity, if you notice the higher force curves, is at a lower velocity. The second thing to observe here is that the barrier to wear, or EW, is lower for higher applied forces, or the normal force reduces the barrier for wear. So while the normal force helps with bonding and increasing the population of species attached to the tip, like we saw in the previous experiment, it also reduces the barrier to wear. In summary, both normal force and lateral force increase the wear rate. While the experiments are in line with other studies, the proposed model disagrees with many other descriptions of atomic scale wear, in which a moving tip breaks the bond from the surface, binds to the molecule, and then carries it away. In our experiments, the forces applied are very low for such direct mechanochemical bond breaking to happen. So what we are saying is wear is a dynamic process in which a series of reversible thermally activated reactions are happening simultaneously and are slightly perturbed and biased by the applied loads. We also performed MD simulations of silicon sliding on graphene oxide to reproduce parts of the experiment. We tracked the population of molecules bound to the tip and to the surface. We calculated that the lowest force, which is 1.28 nanonewton in this case, resulted in about 75% of the oxygen molecules getting transferred from the substrate to the tip. And this number increased to 80% for 3.2 nanonewton. We also tracked the velocity of oxygen molecules. Figure E plots the velocity of oxygen molecules against the time step. This is not the velocity of the tip. It's the velocity of the oxygen molecules. What you can see is the normal force does have a significant effect on the velocity of the functional groups, resulting in more wear. In a sense, bonding must happen for subsequent wear to occur, which is a common notion in most of the models. But the difference here is that there is also an unbonding process that's happening simultaneously, and this has to be taken into account to make the model more accurate. And in fact, this allows for wear to occur at low normal loads, which by themselves, without sliding, are considered insufficient to break the bonds. The elegance of our model is perhaps best explained by this slide. We used our equations to extrapolate for velocities and forces outside of our experiment space. This is a contour of the wear rate as a function of normal force on x-axis and the tip velocity or lateral force on the y-axis. The darker blue just means higher wear rates. For low to moderate forces and velocities, which is our experiment space, wear rate increases with both normal load and lateral load. For extremely low normal forces but extremely high velocities, which is the region in the top left, wear becomes barrierless and is dwell time limited. Such systems are actually pretty common or in which the wear rates decrease with increasing velocity, as the dwell time is too short to form bonds with the surface. On the other end of the spectrum, on the bottom right, when the normal force is excessively high, the wear becomes again a barrierless process, but it does not depend on velocity, or it's independent of velocity, which is the case with Archer type wear. In addition to explaining our own experiments, we were also able to recover and rationalize other wear types observed in the literature by using our model. and by imposing their relevant experimental conditions. As our model is based on chemical kinetics, it can be extended to any arbitrary chemical system. Plus, our experimental framework allows us to pull out energy barriers. This then allows us to estimate properties of the energy landscape of the processes driven under the tip. We wish to further validate this model across spatial scales by exploring a wider velocity range and by also applying higher normal forces to reproduce real operating conditions. We also wish to extend this study to other 2D materials and also to systems in which wear is a multi-physical process, such as high temperature wear or electrochemical wear. Before I end the talk, I want to take this opportunity to talk about the facilities we have at ORNL. CNMS is a user facility where we invite people across the globe to perform their studies. I personally develop AFM platforms to drive and investigate 2D and 3D nanoscale chemical transformations driven by heat, light, electric field, and forces. I encourage you to reach out to me to discuss your projects that you may have in your mind. We have equipment for almost any kind of characterization here. We also have unique capabilities such as AFM with a mass spectrometer to perform in situ chemistry measurements or mass measurements at the nanoscale, band excitation modes and general modes to look at nanoscale electrochemical phenomena, and we also heavily focus on integrating theory and modeling with fully automated experiments. Typically, user proposals are 2-pagers and externally reviewed. Scientist's time and the instrument time are free of charge, and the user just has to take care of the travel and stay here. Once again, please feel free to contact me with your questions and we can discuss about your projects. Finally, before I end the talk, I would like to thank all the other authors who have contributed to this work equally importantly. I especially want to thank Dr. Phelps for investing his time and effort on me at grad school. I also want to thank Dr. Ye for his molecular dynamics simulations. We also thank NSF and TEAS for funding our research. And finally, I thank you for your time and patience in listening to my talk, and I hope you have a wonderful time ahead.